Hi, I hope you've already studied circles, ellipses, hyperbolas, and parabolas. In this video, I just want to talk about them as a whole. The graph of the equation ax squared plus cy squared plus dx plus ey plus f equals 0, where a and c are both not 0, is a conic section or a degenerate conic section. I'll address degenerate conic sections in a few minutes, but the purpose of this video is not to handle those special cases. I want to talk about how you can determine which conic section you have when it's in the general form that you see there. And then you could do some work to transform the conic section into its standard form. So let's look at this. If you're looking at an equation of a conic section in general form, if A equals C, then we'll have a circle. We'll have an ellipse if A doesn't equal C, but A and C have the same sign. We'll have a hyperbola if A and C have opposite signs, and we'll have a parabola if either A is 0 or C is 0. And remember, up at the beginning, we stated that both A and C cannot be 0 at the same time. Otherwise, we wouldn't have our conic sections. Let's look at some examples. Here's what circles would look like if the equation is in general form, something like this. X squared plus y squared minus 25 equals 0. Notice you could very easily add 25 to both sides and put it in standard form. But here's what I want to point out to you. The coefficient of the x squared and the coefficient of the y squared are each 1. But they don't have to be 1. 7x squared plus 7y squared minus 25 equals 0 would still be a circle. Its radius wouldn't be 5 anymore, but it would still be a circle. This would also have a graph that is a circle. 9x squared plus 9y squared minus 18x plus 11y minus 13 equals 0. You would need to do some work to put it in standard form, but notice the coefficients of the x squared and the y squared are equal. How about an ellipse? How would the equation of an ellipse look in general form? Well, much like a circle. In fact, I often think of an ellipse as a distorted circle. We don't have the balance of the coefficients being the same. They're different, like 2x squared plus y squared minus 25 equals 0. The graph of that equation would be an ellipse, as would this. 3x squared plus 40y squared minus 42x plus 27 equals 0. Notice we don't have any linear term with respect to y, but that doesn't matter. I'm focused on these two coefficients right here. They are the same sign, and they're not equal. So if we were to graph this, it would look like an ellipse. How about equations of hyperbolas? We could have something like 2x squared minus 7y squared minus 28 equals 0. And we look at these coefficients and we see they have opposite signs, so our expectation is that we'd have a hyperbola. Or how about this equation? X squared minus y squared plus 8x minus 4y plus 10 equals 0. You'll notice the coefficients of x squared and y squared are 1 and negative 1. They are opposite signs, so we would expect the graph of that equation to look like a hyperbola. And finally, let's look at the equations of some parabolas. Here's one. 9y squared plus 11x equals 0. If we were to graph that, we would see a parabola. Notice in this case, we have a c value that's equal to 9, but the coefficient of x squared has become 0. That's why we don't see an x squared. Or we could look at this equation. 25x squared plus 3x minus 7y plus 42 equals 0. Again, I have one quadratic term and the other one isn't visible because its coefficient is 0. Before we continue, I just want to talk just a moment about degenerate conic sections. Those are conic sections that would be of the form ax squared plus cy squared plus dx plus ey plus f equals 0, but they don't have graphs that are circles, ellipses, hyperbolas, and parabolas. And I'm not going to do much with them, but let me give you one example. This one, x squared plus y squared equals 0. Certainly, it fits this general form. But if you try to find solutions for this particular equation, you will find that 0, 0 works, and there are no other solutions to it. So the graph of this equation right here would be the single point at the origin. So we would say this is a degenerate conic rather than one of our 4 major conic sections. And there are other examples, but the purpose of this video is not to describe those other degenerate cases. They're entertaining, but I want to focus on circles, ellipses, hyperbolas, and parabolas. Before we do a few practice problems, I wanted to give you a summary of our standard forms for our conic sections. This is just a summary. It doesn't have every detail down that you should know. For example, notice on the lower left, I have the hyperbolas listed there, but I didn't even mention the asymptotes. But let me point out a few important things. Notice in all of the cases, we have x minus h, and we have y minus k. And hk is the center in the circle, ellipse, and hyperbola, and it's the vertex for the parabola. We don't really have a center for a parabola, and the vertex of the parabola kind of plays the role of center in that conic section. So we can always look with our x to find the x-coordinate and look with the y to find the y-coordinate of center or vertex. Notice how similar the equations are for the ellipse and the hyperbola. There are a few distinguishing features, though. Notice with an ellipse we have a plus, and in the hyperbola we have a minus. Also, for an ellipse, the a squared is always the larger of the two denominators. Notice when the a squared was underneath our x squared, our major axis was in the x direction. It was horizontal. When the a squared is underneath our y squared, we have a major axis that is vertical this way. So the a squared is always the larger of the two denominators when the equation of the ellipse is in standard form. Now let's come over here to our hyperbola. Look at these two equations. Notice the a squared is the denominator of the first term. It may or may not be larger than the b squared. So the a squared gives us the distance from center to vertex. Center to vertex is A. Center to vertex is A. Doesn't matter whether the hyperbola opens right and left, as in this case, or opens up and down in this case. Similarly, over here on the ellipse, the distance from center to the vertex was A here, and it was A here as well. Also notice that with an ellipse, we have a plus here, but when we come down to the relationship between A's, B's, and C's, we have a minus. Over here with hyperbolas, we have a minus, and the relationship between A's, B's, and C's, we have a plus. So I just keep that in mind. These signs are in opposition. A plus and a minus and a plus, and it helps me remember those. Now, over here on the parabolas, look at the vertex, always at HK. If we have a y equals x squared type, we have something that will open up or open down, depending on whether the coefficient is a positive 4a or a negative 4a. Similarly, if we have an x equals y squared type, we have a parabola that opens right or left, and then that's determined again based on whether the coefficient is positive 4a or negative 4a. Remember, for a parabola, the distance from vertex to focus is a units, and the distance from vertex to directrix is a units as well. I just wanted you to see this summary before we do a few problems. Let's do this problem. The equation is y squared minus 10x minus 8y plus 21 equals 0. Part A is to write the equation in standard form for this particular conic section. So we need to know what conic section that we have. Do you recognize that it's going to be a parabola? Because we have one quadratic term, we do not have another one. In other words, we have a y squared, but we don't have an x squared. So I expect it to look something like this. Y squared equals plus or minus 4ax. I don't know whether the coefficient of x is going to be positive or negative, but I'm thinking about this. And notice I didn't even shift it off the origin. Really, I'm expecting it to look like this. Y minus k squared equals plus or minus 4a times x minus h. So let's go. Let's put it in that form. Notice to do that, I need the perfect square on the left and everything else on the right. Let's do that. I'll have y squared minus 8y on the left, and I'm going to add 10x and subtract 21, so those terms are now on the right. I left the negative 8y on the left because I know I'm going to complete the square with respect to y. Half of negative 8 is negative 4. Negative 4 squared is 16. So I add 16 to both sides. Now I have a perfect square on the left. It's y minus 4 squared. And on the right-hand side, I have 10x minus 5. Now notice, in order for it to look like this, I need to factor out the coefficient of x. So inside the parentheses, you'll just see a 1x. That means I'm going to have to factor out a 10. And this is why I wanted you to see this example, because sometimes people get concerned that they don't have a common factor of 10. That's okay. We're still required to factor out the 10. Well, if we factored out a 10 and we just had a 5, what would we have left? Well, we would just divide that 5 by 10. Notice this. If I were to distribute 10 times 5 over 10, those 10s would cancel, and I would have that negative 5. So my equation is really y minus 4 squared equals 10 times x minus 1/2. And I have the equation in standard form. Now there is a part B. I didn't want to put the part B down because that would give away what kind of a conic section it is. So let's state the coordinates of the vertex and focus and write the equation of the directrix. So let's start with the vertex. We know the coordinates of the vertex are looking at us right here. The x-coordinate is with this x and the y-coordinate is with the y. So our coordinates of our vertex are 1/2, 4. And I like to sketch the curve because it helps me find the focus and directrix. So let's do that. Let's see, 1/2, 4. I'll put my 1 here, so a half will be right here and up at 4. So here's my vertex right here at 1/2, 4. I know this is opening to the right because we have an x equals y squared type, and the coefficient here is positive. So I'm just lightly doing this. It doesn't matter how wide or narrow I have it because the goal is just to find the focus. It just helps me think it through. So my focus is over here somewhere, and my directrix is over here somewhere. I need this distance right here because if I knew that distance, I could tell where the focus is. Well, we know that is A. And for this problem, I know that 4A is 10. Let's use that information. 4A equals 10 means that A is 5/2, or 2.5. So if I start at the vertex, that is at 1/2, 4, and I move to the right 2.5, that will put me at 3. So this point right here is at 1/2 plus 5/2, comma 4, which is 3, 4. That's our focus. Now for the directrix, we go 2.5 to the left. So starting at 1/2, I move to the left 2.5, and I would be over here at -2. We know the equation of a vertical line is always x equals something, so in fact it's x equals -2. Let's write that. Directrix has an equation that is x equals -2. Let's look at this next example. 2x squared minus 25y squared minus 24x minus 50y minus 3 equals 0. It's in general form, and our goal is to write it in standard form. Do you know what conic section it is? Are you looking right here? It's a 2, the coefficient is a 2, and a -25. Since A and C are opposite in signs, we know we have a hyperbola. So I know I'm going to make it look something like this. X minus h squared over a squared minus y minus k squared over b squared equals 1. Or the x minus h squared and the y minus k squared could be switched around. I don't know, but it will be revealed as we start completing the square. So let's do this problem. I'm going to complete the square with respect to both x and y. So let's put the terms with the x together. So we have a 2x squared minus a 24x. I'm going to leave a space, and I have a -25y squared minus 50y. I don't want the -3 to be involved in completing the square, so I'm going to add 3 to both sides so that the 3 ends up on the right-hand side. In order to complete the square, I need to factor out the coefficients of the quadratic term. So I'm going to factor out the 2, and I'm going to factor out the -25. So let's do that. We have 2 times x squared minus 12x. And we have a -25 times y squared plus 2y. Take care with that sign. When you factor out a negative, it will change the sign right here. And we still have the 3 on the right-hand side. So now I'm completing the square. I take half of negative 12, that's negative 6. Negative 6 squared is 36, so I need to add 36. But notice that's not a real 36, that's a 36 times 2. I've really just added 72 to the left-hand side, so I need to add 72 to the right-hand side. Right here, I need to add a number. I'm going to take half of 2, that's 1. 1 squared is 1, so I need a 1 right here. But what did I really just add? I added a 1 times negative 25. I've really just added a negative 25, so I need to add a negative 25 to the other side as well. So my equation will now look like this. 2 times x minus 6 squared minus 25 times y plus 1 squared equals, what is that, 50? Remember, I need a 1 on the right-hand side when I'm putting it in standard form for a hyperbola, so I'm going to divide by 50. Divide both sides by 50. And my equation becomes this. X minus, let me change color. X minus 6 squared over 25 minus y plus 1 squared over 2 equals 1. And I have the equation written in standard form. And again, there's a part B. Let me write what that is. We'll find the coordinates of the center, vertices, and foci, and then we'll write the equations of the asymptotes. So I'm going to slide this up so I have more space. I'm going to make sure that we can still see that standard form of the equation though. So let's begin. Do you recognize the center? We are looking right here, 6 and negative 1. So let's write that down. Center is 6, negative 1. And it doesn't ask me to sketch it, but I find it very helpful to do that. Helps me think it through. So 6, negative 1. I'm going to put my center right here. And notice the x squared is first, so I know this is going to be opening right and left. So I look underneath the first term, and I can see how far to go in the x direction. The 25 is underneath the x squared, so I'm going to go in the x direction 5 units. And those will be the vertices. So from center, I'm going to move 5 to the right. That will put me here at 11. And 5 to the left, that will put me here at, positive 1. I was about to write a negative 1 there. So I have one vertex at 1, negative 1, and one vertex at 11, negative 1. I'm just going to erase that. That's just a little bit too unreadable here. So my hyperbola, I know, is going to open this direction. Just helps me think it through. So let's write our vertices. They are 1, negative 1, and 11, negative 1. Let's move on. We need to find the foci. One focus is inside this branch of the hyperbola, and one focus will be in this branch. I don't know where they are, but I do know they are C units from center. Here's my center at 6, negative 1. So I need to find C. Well, let's jot down what we know. We know that a squared was equal to 25. It's right here. The denominator of the first term. I know that b squared is right here, 2. So let's write that down. So b squared equals 2. I know the relationship between a's, b's, and c's in a hyperbola is a squared plus b squared equals c squared. So let me pop in the numbers. I have 25 plus 2 equals c squared. So 27 equals c squared, and when we take the square root of 27, we get 3 square root of 3. So I know I go in the x direction, horizontally, 3 square root of 3 to get over here. That means I'm going to add 3 square root of 3 to the 6. So it's 6 plus 3 square root of 3, comma negative 1. And then over here, I'm subtracting 3 square root of 3 because I'm moving to the left 3 square root of 3. So this one will be 6 minus 3 square root of 3, negative 1. And let's put those up here with the other information. So the foci are at 6 minus 3 square root of 3, negative 1. And 6 plus 3 square root of 3, negative 1. Now I have, what do I have left? Oh, I have to find the equations of the asymptotes. How would I do that? Well, I already have gone a units from center and found these vertices. I need to move b units from center so that I can draw my central box. What is b? Well, b is the square root of this number, so the square root of 2. Well, that's not a nice number. Well, it's irrational, but it's totally valid. I'm going to go up square root of 2 units and down square root of 2 units. My scales aren't quite the same in the x direction and y direction, but that's okay. This is just a little sketch here to help me think it through. So I'm going up square root of 2 and down. From this center point, I went up square root of 2 units and down square root of 2 units. So here's my central box. Right here. Here's why this is important. Because remember, the diagonals of this central box can be extended and you will have your asymptotes. Same thing over here. So what are the slopes of those asymptotes? The rise is square root of 2. And the run, remember slope is rise over run, is 5. So the slope of this line is the square root of 2 over 5. And of course, that means the slope of this line is negative square root of 2 over 5. Now that doesn't answer the question, what's the equation of the asymptotes? So here we go. Let me remind you what point slope form is for the equation of a line. It's y minus y1 equals m times x minus x1. So when we're looking for the asymptotes, we can use that formula. I know the slopes are square root of 2 over 5 and negative square root of 2 over 5. We know the asymptotes must go through center. So let's write it out. Asymptotes. The point they go through is 6, negative 1. Their slopes are plus or minus the square root of 2 over 5. So here we go. Y minus negative 1 equals the square root of 2 over 5 times x minus 6. There's one asymptote. And we have y plus 1 equals a negative square root of 2 over 5 times x minus 6. And that's our other asymptote. This was just the information that we were using to find these asymptotes. Here are our asymptotes. Now, I'm going to leave them in point slope form. If you needed them in another form, you could distribute and make them look different. Let's do one final problem. This time we're going to find the equation of a conic section. We're going to find the standard form of the equation of an ellipse with center 51, 4, vertex 51, 11, and focus 51, 1. Now notice I just gave you one vertex, and of course we have two vertices for ellipse. Similarly, I gave you one focus, and we know there is another focus, but this is enough information for us to be able to come up with the equation. Remember, the equation of our ellipse will look like x minus h squared over a squared plus y minus k squared over b squared equals 1, or the a squared and the b squared will be switched around. But that doesn't matter right now. I know I'm shooting for something that looks like this. I told you I like to start with a sketch, so I'm going to do that. 51, 4. 51, where will that be? It doesn't really matter. 51, right here. I don't need the scale in the x direction and the y direction to be the same. So let's see, 51, 4, I'll put that right here. Here's my center. Vertex at 51, 11, so up here. 51, 11. I'm just making note of the fact that it is 7 units higher than the center. That means the other vertex would be 7 units lower. I'm just going to put it in there because it makes me feel better if I do that. Not really necessary, but I feel better if I have that there. Now the focus, one of the foci is at 51, 1. So let's see, 51, 1 would be about right here. And I notice it is 3 units below the center. That means there's going to be another focus up here, 3 units above center, 51, 7. So that's up here at 7. This is here at 1. And I know that my major axis is vertical. So I could draw a rough sketch of this ellipse looking something like this. So I know now that my A's and B's are actually in the other order. They should be switched because the bigger number will be underneath the y squared. So let's write what we know so far. We know it will be x minus the x coordinate of the center, 51, squared over b squared, plus y minus the y coordinate of center, that's 4, squared over a squared equals 1. So I just need to find a squared and b squared. Let's look back at our picture. We know the distance from center to vertex is a. From 51.4 up to 51.11 is 7 units. So let me write that down. A equals 7. That means a squared equals 49. We also know the distance from center to focus is c. So c is equal to 3 for this problem. So let's write that. If c is equal to 3, that means c squared is equal to 9. All I need to do now is figure out what b squared is. I have my a squared. I could fill that in. I'll do that in a minute. I need to figure out b squared. So let's come down here and do it. We know the relationship between a's, b's, and c's with an ellipse is a squared minus b squared equals c squared. I'm popping in my a squared, and I'm going to pop in my c squared. And I solve for b squared. So I'm going to add b squared to bring it to the right and subtract 9 and bring it to the left. So I have b squared equals 40. So my equation can now be complete. I'm going to substitute the a squared and the b squared in. So I have x minus 51 squared over 40 plus y minus 4 squared over 49 equals 1. And I have the equation of the ellipse described. I hope you'll go do some practice with some conic sections.